What if humanity achieved something that scientists have considered literally impossible for more than a century, traveling faster than the speed of light? I mean, right now, even the nearest star system would take thousands of years to reach with our current technology. But today, we're going to explore the ultimate science fiction dream, traversing the cosmos faster than the absolute speed limit of the universe.
Just imagine a future where a revolutionary breakthrough allows spacecraft to cross entire galaxies in days instead of millions of years. Suddenly, distant planets would become destinations, not just dreams, and humanity could spread across the cosmos faster than ever imagined. New civilizations might emerge on alien worlds, and the Milky Way could become our new home. Before we continue, if you're enjoying these mind-bending future scenarios, make sure to like this video, share it with a friend, and subscribe to Last Human Era for more incredible journeys into the future. Now, let's dive into this explainer and see if crossing these unimaginable distances is actually physically possible or, just a mathematical fantasy. Section 1. The speed limit of space.
Okay, so to understand true faster-than-light travel, we kind of have to strip away the illusions first. This brings us to what physicists call trivial FTL. Like if you cast a shadow or sweep a laser pointer across the moon, the spot of light might actually move across the lunar surface faster than the speed of light. Or think about the Cherenkov effect, where particles travel faster than light does when it's moving through water. But here's the catch. None of these phenomena actually carry usable information or physical energy faster than light in a vacuum. They're essentially just optical illusions or context-dependent tricks of physics.
So, the absolutely crucial point here is defining true faster-than-light, or FTL, travel. We are talking about the theoretical propagation of actual, usable information or a physical spaceship faster than c, the absolute speed limit of the universe, which is roughly 300 million meters per second. Now, according to Einstein's special relativity, as an object with mass accelerates closer to this absolute limit, its energy requirements start approaching infinity. To actually reach c, it would require an infinite amount of energy. So simply pushing a massive rocket through space is, well, entirely out of the question.
Section 2. Biology at light speed.
Let's think about the physical reality for a second. What would actually happen to the human body if we somehow tried to reach these unbelievable relativistic speeds through conventional means? Well, if you're moving at a constant velocity, even at like 99.99% the speed of light, your body wouldn't feel a thing. The laws of physics dictate that constant motion is physically indistinguishable from standing perfectly still. But getting up to that speed, that's the real issue. The violent, crushing g-forces required to accelerate a human being up to near light speed within a normal human lifetime would be completely lethal. Our bodies simply aren't built for sustained acceleration much beyond Earth's gravity of 9.8 meters per second squared.
And actually, there's a hidden biological danger lurking in the vacuum of space. As humans venture deeper into space at near-light speeds, the cosmic microwave background radiation that permeates the entire universe actually blue shifts from your perspective. It compresses into deadly, highly energetic gamma rays that are nearly impossible to shield against. At those extreme speeds, even a microscopic speck of cosmic dust would hit your ship with catastrophic force. We'd be venturing into regions of the universe no human was ever meant to see.
Section 3. Warping space and time.
So, since we obviously can't accelerate through space without dying from g-forces or radiation, we have to rely on a brilliant mathematical loophole, moving space itself. This brings us to the famous 1994 Alcubierre warp drive model. Instead of firing a rocket, the ship theoretically compresses spacetime ahead of it, creating positive curvature, and expands spacetime behind it, creating negative curvature. The ship itself stays locally stationary inside a flat, protected warp bubble. You're essentially surfing a wave of violently stretching and compressing spacetime. It's genius, really, because it perfectly bypasses the lethal acceleration and infinite energy problems of special relativity.
But there was a massive original catch. Alcubierre's math worked perfectly on paper, but to create that negative curvature behind the ship, it required an utterly impossible amount of negative energy. We're talking 10 to the power of 62 joules of exotic matter. To put that into perspective, that is vastly more energy than exists in the entire observable universe. And it's made of a substance we aren't even sure actually exists.
Section 4. Solving the energy crisis.
This is where cutting-edge modern physics steps in to solve that negative energy roadblock. First, physicist Harold Sonny White used a mathematical framework called the ADM 3+1 formalism to update the original design. Instead of a continuous, smooth ring of exotic matter around the ship, he proved that a segmented, cylinder-shaped structure could actually stabilize the flat interior of the warp bubble.
And interestingly enough, this segmented design bears a striking physical resemblance to the propulsion rings we see on fictional spacecraft in Star Trek. Pretty cool, right? But the real game changer here is a massive theoretical breakthrough by physicist B. Keogh. Keogh discovered a method using generalized gauge transformations to directly convert the electromagnetic tensor into the Weyl tensor. Okay, in plain English, it means we might be able to control space-time curvature using precisely manipulated electromagnetic fields, completely eliminating the need for that mythical, impossible exotic matter.
Just look at this mind-blowing reduction. By using electromagnetic manipulation, Chow's calculations reduced the energy requirement for a realistically sized 20-meter diameter warp bubble from that impossible 10 to the 62 joules down to just 4.9 million joules. Seriously, 4.9 million. That changes literally everything, bringing faster-than-light travel out of the realm of pure fantasy and straight into the realm of physical possibility.
Section 5. The Time Travel Paradox.
But breaking the speed of light could come with unexpected consequences. The Alcubierre drive has a major flaw. The crew inside the bubble is causally disconnected from the outside wall, meaning they can't actually steer or stop the ship once it's moving. Enter the Krasnikov tube. Instead of a bubble, a ship traveling just below light speed lays down a permanent subway track behind it. Inside this tube, space-time is flat, but the light cones are opened out, allowing a superluminal return trip. Basically, you build the road on the way there and take the express train back.
However, some theories suggest this might affect time itself, creating paradoxes that challenge our understanding of reality. Connecting two non-overlapping Krasnikov tubes, or making round trips at superluminal speeds between warp bubbles, theoretically generates what physicists call closed time-like curves. Entire societies could become separated by different timelines, and humanity may face dangers more advanced than anything on Earth. The very laws of physics that hold the universe together could begin to reveal hidden secrets, specifically that you've just built a literal time machine.
Now, to avoid the famous grandfather paradox where you go back in time and accidentally erase your own existence, the universe might actually have a built-in defense mechanism. Stephen Hawking proposed the chronology protection conjecture, suggesting that quantum effects like divergent vacuum polarization would violently destroy any space-time structure attempting to create a time paradox, thus protecting the history of the universe. Furthermore, as some mathematical models show, just because you have FTL motion, it doesn't strictly guarantee time travel is even possible. And if these future possibilities fascinate you, don't forget to like, share, and subscribe because every week we explore the most incredible futures humanity may face. In the end, faster-than-light travel wouldn't just change transportation, it would completely transform humanity's destiny, turning us from a planetary species into a truly cosmic civilization. But if you had the chance to board the first faster-than-light ship and leave Earth forever, risking the fundamental rules of time itself, would you take the journey or stay on the only world you've ever known?